Okay, welcome. My name is Geert Demortier. Since 5 years, I've been head of the group at the national regulator PANC that deals with environmental protection, radiation, and emergency preparedness, so preparing for incidents and accidents. And it's in that respect that I'm here to talk about risk assessment in remediation, because remediation is obviously part of, well, the final step of looking at reducing risk in certain situations. And more specifically, it's about remediation in norm. I think you've had some notions of what norm is this week, but just in case, a little lesson in natural radioactivity. So it's naturally occurring radioactive material. There is radioactivity in our environment. It's there because, well, stars produce a lot of different elements, and some of them are radioactive. And uranium-238 is the main natural radioactive nuclide, and it has a decay chain that by now you probably have heard of, which contains radionuclides like radium, radon gas, lead-210, and polonium-210. There's also thorium series with another form of radium, but just it's a cocktail of alpha emitters, beta emitters, and gamma emitters. And they are present in our environment in low concentrations, depending on the country you're from. They might be slightly higher because geology is different. But the important part is that they all have a different chemical behavior. And in situations where the chemical behavior matters, that's when it becomes interesting. So there are a lot of classic industries, metal producing industries, phosphate industry, which we'll see in a moment, that use ores, water, oil, and so on, that also contain natural radioactivity in some form. If you put them in a process, in a chemical process, typically to, for example, get phosphates from rock, then it might happen that some of these radionuclides will concentrate with those phosphates into your residues, into the end products, or sometimes in waste. And so protecting workers, the environment, and the public from these sources of radiation, that's risk management in norm. Now, in Belgium, most of the norm industries, historical norm industries, are concentrated here, which is, well, not exactly the region you're in here, but a bit to the east, to the west, sorry. It's early morning. And there's a lot of phosphate industry that was actually put there. There's also radium industry, which I won't talk here, but just remember all the heavy industries were put in that region because at the time, beginning of the 20th century, there weren't that many people around, and so a lot of international industrial groups thought it was a good idea to put their factories there. And so, since 1880, there has been a factory in a town called Tessenderlo and Ham that was producing chemical components, among which phosphate. Obviously, from a factory, you get liquid releases, you get discharges into the environment that normally are controlled. But obviously, it was 1880 to 1840, and so there wasn't a lot of environmental control around, because people weren't really thinking about environmental protection until the 70s. And so for 100 years approximately, they released their liquid discharges from their process into two small rivers called Winterbeek and Grote Laak, which go on into two larger rivers, the Demer, which is flowing next door, I think, and the Nete, which is to the north. But ultimately, they all end up in the Schelde. And the Schelde is a large river that passes by Antwerp, and Antwerp is a city with 500,000 inhabitants. So it all ends up flowing to the estuary of the Schelde. Now, the problem with phosphate industry is that they use sedimentary phosphate ore. Sedimentary phosphate ore is formed in conditions where you have a shallow sea with microorganisms that make little shells diatoms, and so on. And some of them have phosphate components. Phosphate components attract uranium. Uranium binds very well with phosphate components. So in these sedimentary phosphate ores, you get a high concentration of uranium. And if you get a few million years, then you get equilibrium between the decay chain of uranium and uranium. And so you end up with 1 to 2 becquerels per gram of uranium chain, 1 to 2 becquerels per gram of uranium, radium, polonium, and lead, and so on. And so the main problem is that you try to make, phosphate fertilizers, and you end up in the process with some residues like calcium sludge, calcium fluoride sludge in ponds. So this is a residue product that you have to deal with. You end up with calcium chlorides in effluent water. Those are the ones that were released in the rivers. And radium has the nasty habit of following calcium, because in the periodic table, calcium and radium are quite close. So radium is a radioactive nuclide in very low chemical concentrations, but it will follow calcium. And so any component, residual component here that has calcium will also contain radium. So you have radium chlorides, radium fluoride sludge, and scalings. And scalings are inside the factory. You have to see it as white, well, hard crust inside. You can see in the installations there. Those are very high concentrations of calcium sulfide, which will also contain radium. So you have a radiation protection problem inside the factory, but what we will focus on in this presentation is what happens outside the factory. So until 1990, remember this factory was there since 1880, producing phosphate fertilizers. You would get 20 to 30 becquerels per liter of radium-226 discharged in those 2 rivers. Now, that's 7 grams of radium per year. So you would say 7 grams, that's not much. Marie Curie, who discovered radium and tried to extract radium from phosphate rock, phosphate ore and uranium ore in big, reaction vessels in her life, did not isolate this much in her entire career. So 7 grams of radium is a lot. And it's actually, I think in the whole history of radium extraction, it's really extracting radium for radium paint, for example, and other applications, radioactive applications. You don't get to 100 grams in the entire history of radium extraction. So this factory was releasing 7 grams a year from its process. Now, in the 60s, the predecessors of the people working at SCK now realized that, there were some indications that radium was a problem in phosphate industry, and they started to look at the contamination. So in the 60s, in what was a very early SCK, people like Dr. Kirchmann, and those are still basic studies that are still very valuable, start to look at contamination. In 1990s, up to 2013, the process was changed. So up to 1990, all radium, most of the radium was discharged in rivers. So in 1990, the environmental permit of the factory had to be renewed. And then due to also the presence of a lot of heavy metals, obviously, in those discharge waters, the environmental regulator on the Flemish level said, for your permit to be renewed for your factory, you need to reduce the metal levels in your discharge water. And so they tried to find a process where you co-precipitate with barium. Obviously, that moves all the radium and all the metals to the sludge that you can put in one location, but it doesn't disappear. You just concentrate it at another location, but you reduce the amount of contamination that goes into the river. In 2014, the permit had to be renewed again. And at that point, the environmental regulator on the Flemish level said, you have to reduce your metals even more and the salts, or you have to close. And so economically, they had to make a decision: do we continue, but do we invest in reducing our pollution in the discharges even more, or do we close our factory? And they closed the factory. So what I'm about to tell is the legacy that comes from those discharges and how you clean it up. Just to give an idea about changing the technique of co-precipitation, it reduces drastically the amount of pollution that goes into the discharge. So this is the story mainly about, well, this river here to the south and how it was cleaned up. But first we have to tell how it got contaminated, because you release discharge water in a river, that contaminates the riverbed. How does the riverbed contaminate the river banks? Well, there is obviously also a lot of agriculture in this region. And so if you get discharges in a river and sediments pile up, and at a certain point the river goes onto the river banks because the flooding frequency increases. And so the regional authorities decided between the 70s and the 90s that occasionally they have to dredge the river and put the sludge, well, the sediments on the river banks, which was not an entirely good idea, because then you contaminate the riverbanks and then you get leaching into the soil on the riverbanks. For the Winterbeek, in this case, it resulted in 17 kilometers of contamination on both riverbanks with heavy metals and radium, because you get a cocktail of heavy metals and radium. There are flooding areas as well, because you get occasional flooding, and if you have releases at that moment, obviously you directly contaminate the river banks. And to give an idea how much contaminated soil we're talking about, it's approximately 200,000 cubic meters of sediment and soil that had to be dealt with. So this is what you're dealing with in the beginning. You can start characterizing your site. So what does it look like in practice? And this is a helicopter measurements with what is called an AGS, a Euro gamma spectrometer. You put a detector on the helicopter, you fly above your site, and then you get an idea where your spots are. This big spot on the top is the sludge heap where they put their sludge now, so they concentrate their sludge now. What we're actually looking at, and which is interesting for the rest of the story, is the release points and what you get downstream. So you can see that for the Winterbeek here, you get large zones of contaminated riverbanks, and at the end you have a swamp where you have a kind of a wetland system, and there obviously it's kind of a sink for contamination. Somebody from SAK at the time also went there on foot, and then you see that the helicopter view, if you detail it, it might be a bit more complex, because obviously in a wetland you get interactions and canals and so on. So this is what we're dealing with. Of course, reducing contamination, it's a multi-tiered step process. I mean, you first have to know what is there, how much is there. That's what we are looking at in the previous slide. Then you have to assess the risk, and then you have to see, okay, who are my stakeholders in the neighborhood? What do they think about acceptable risk? What risk is acceptable? Do they want zero risk? It does not exist. How are we going to deal with the options we have to clean it up? And you end up with a remediation project. And that remediation project has to take into account all factors that you have discussed with your stakeholders, but also the risk and the ways you reduce risk. Reducing risk does not mean that there is residual risk. There isn't any residual risk. So you have to have a strategy for post-remediation management. So what exactly are we looking at? Well, there are two riverbanks in this case, and you can see that the concentrations are, well, in the same range, somewhere between 1 to 10 becquerels per gram. And the average is approximately the same. The amount of contaminated soil on both riverbanks is not the same. It's not pictured here. But one of the riverbanks, it's very difficult terrain to access for example, dredging engines. So you have a crane that pulls sediment from the river. There's only one side where it's really easy to do so. So you get a bit of a mismatch between two riverbanks, but that's you have to study them, both of them anyway. And then you do a dose assessment. And I think you've seen during the week how you do a dose assessment. You ultimately have to calculate those with an exposure model. Is there any fishing? Do people walk on the sites? Are there any activities that might result in those? Do people eat vegetables that might be contaminated, and so on? And you build a model of exposure. Now, if you do this for this site, where there is a lot of woodland, there's a lot of wetland where nobody lives, actually you end up below 1 millisievert a year. So is remediation, do you have to start digging because you have one lower than 1 millisievert per year? No, because actually starting to dig, if you start to remediate, you create exposure of workers, and so you actually make the problem worse temporarily. So you have to bring that again into balance. And so from a radiation protection point of view, in that region, you could leave it there with some measures of protection. Of course, if you build a house on top of radium contamination, then you get a radon risk, because that radioactive gas can dissipate, and then you get millisieverts and a lot of millisieverts of exposure. So you have to take measures, administrative measures, to make sure that people don't build on those sites. You can look at workers, and well, there are rat catchers, or there were rat catchers in the neighborhoods who spend a lot of time on the site. Again, wearing dosimeters, there was not really a lot of exposure. SEK studied the impact to biota. They found some impact, but again, impact to biota is not in national legislation. It's not a factor that you have to look at for radioactivity. Obviously, you have to do it for chemicals. So they found some effects on invertebrates, but that does not trigger large-scale remediation. What about the chemicals, though? And if you look at the main pollutant that was the problem, it's cadmium. You had up to 160 milligrams per kilogram of cadmium. And if you look at the zones where the cadmium is highest, if you remember the dose rates and the radioactive scanning done on foot and with the helicopter, you can see that the pattern is actually quite similar. And so, actually, in this case, we could demonstrate that everything above 150 nanosieverts per hour contains 90% of the samples that were above 6 milligrams per kilogram, which is in regional environmental legislation a limit, actually the remediation limit for that type of area. So you can use those rates to look for metals, because radium and cadmium actually correlate in where they can be found, which is logical, because you get heavy metals. Radium is a heavy metal as well, and it will in some ways be found at the same locations. Obviously, for the regional authority, which deals with the chemicals in soil, we're a federal authority, we deal with the radioactivity in soil. The regional authority said, well, this is above this level. Remediation has to take place, and so intervention is needed. So they decided that a cleanup of the site was needed, and so we had to follow. Now, this is the kind of model you deal with to look at impact. I should have put the slide a bit earlier. But again, you look at different exposure routes. You try to quantify those exposure routes, and you try to be as conservative as possible in your approach. Do people live on contaminated soil in practice? No, but you can calculate as if they are living there, as if they are having vegetables in their garden, and ultimately you end up with an individual dose. Now, at the time in 2015, there was no federal framework to deal with radiologically contaminated soils. By chance, 2 days ago, we published one, so now we have one. But in 2015, when we were looking at this problem, there was no legal framework. So the entire justification of remediation depended on the heavy metals. Those are a regional competence of the regional soil authorities. And so just by starting to remediate, as I said, you create exposure. So you want to clean it up. There's no justification to actually clean it up because the exposure in practice to the public isn't high, but you have another justification to start cleaning it up. And so you create exposure. That's something we have to manage. So we use our legislation for natural radioactivity, which says that anything that is above 0.5 becquerels per gram of radium, if you start working with it, with material or soil or whatever, you have to declare it to FUNC, and FUNC are my company, the authority I work for, has to look at the impact study to the workers. And so if you have a remediation project, you have to look what the impact is to workers that have to dig, that have to remove the soil, put it in a truck, drive it to a site where you store everything, and then you have to have an impact assessment for that site. So if we looked at the dose in those cases is above 1 millisievert per year, we start to impose measures, wearing masks, cleaning your cars, your equipment, and so on, doing groundwater monitoring on the site where you leave your soil, and so on. Of course, we've characterized the site. We've evaluated that there will be a remediation project, because for chemical components, you have to do it. And then there is a stakeholder discussion, and the stakeholder discussion has to balance the science, how much risk is there, with your stakeholders' opinions. And stakeholders' opinions can be the local community, can be the mayor of whatever community you have there, can be the inhabitants nearby, it can be the local rat catchers for all you want. It will be all the regional authorities that are involved. So it's the river, the one that deals with the river, the soil authority on the Flemish level, and so on. And you have to bring them around the table, and you have to determine the available options and techniques that are there to reduce the risk for the chemicals and reduce the risk for radioactivity. You have to determine what the boundary conditions are for each technique. In which case can we use it? What will the effect be? Are there any secondary effects, and so on? And you have to do this for every type of plot, because you will have very valuable Natura 2000 and bird directive and habitat directive plots. I mean, you have nature reserves that are very valuable and have value, intrinsic ecological value. But how do you balance ecological value with radiological risk or chemical risk? And that's the thing here, that it's very difficult. For each option and technique you have, if you apply it, you have to apply a cost, and not just the economical cost, what does it cost to apply it, but also the cost for whatever you have there now. If you have a nature reserve and you start digging, then you remove your ecological value, and that has a cost. And so you have to balance it. And this has to be done in a BATNEC evaluation. So best available techniques, not entailing excessive economic costs. So then I always mess up my acronyms. So what are the options actually here? You can remove soil. That's a very, if you ask people what is remediation, soil remediation, they'll say, well, soil removal, just start removing everything. If you look at what happened in Fukushima, Japan started removing the topsoil of contaminated zones, put it in big bags, and put it in one location. By removing topsoil, you also remove the most valuable part of your soil. So if you want to reinstall agriculture afterwards, that's a problem. So that's the cost of that option. You can try immobilize contamination in the soil. There are different techniques. You can try phytoremediation as a technique that works in some cases. It might not work in others. You can do nothing. Well, nothing, no intervention, but you can monitor and try to look at problems when they arise. If land use changes, you have to take measures. That has a cost as well, because you need to monitor. And you can also impose recommendations on land use. So you can say, well, if you put sheep, just don't eat the sheep, for example. You can. That's a measure that was actually applied here, because you need to. There are some meadows that had to be kept as meadows, and the best option was to put sheep there. But then you have to take measures regarding those sheep and so on. So every action has to be evaluated according to its effect and its cost. And the effect might differ for radionuclides or for other chemicals. So you have to look at radiation protection and chemical protection. And all this information has to end up in a stakeholder discussion. And this is what you end up in practice. So you have different, it's in Flemish, but you have meadows, you have forests, you have urban areas. Well, urban areas, you have small clusters of houses and so on. And you can start digging, that's the first column. And in most cases, there are 3 pluses because you remove the contamination, so the risk is removed. But obviously, if you start digging in very valuable types of land, like ecological value, then the minuses start to show up. And you can do this for immobilization, phytostabilization, which is always a good idea because you can put plants and you make sure that the contamination doesn't spread. There's less erosion. You can do monitoring, which is also a good idea. And if you see this column, which is solidification, you see minuses. Why? Well, you put a kind of a substance in the ground that renders everything immobile and unavailable to any biota whatsoever. So if you use this, then there's obviously a cost to that. This is not an easy exercise because the pluses and the minuses are, well, can be subjective. I mean, this is part of a discussion, and you end up with a discussion and a kind of a compromise in best case. So once you do this, you can start calculating the costs. You can put the project in practice. And this is what happened in practice. So they started digging up to a certain level. They used those rates to look at the chemical levels. If they ended up to a certain dose rate, they stopped because they knew that all the metals were gone. And all the soil went to an existing landfill of the phosphate plant, which took back the contamination, but then you obviously have to monitor the landfill site. In some cases, it wasn't possible to do things as planned because you end up with a groundwater table. You can't start digging below the groundwater table, or you end up with, for example, a geological layer that you hadn't planned looking at. And so in practice, your remediation project along the way has to be modified compared to the reality in the field. So there are limitations. I mean, accessibility is one. If you want to go to a plot of land where you have to start digging, but with all your heavy machinery, you have to cross a large ecological reserve. Well, that's not a good idea. So accessibility is a limitation. Groundwater I've just mentioned. And obviously you can't start digging in habitat and bird directive sites because that would remove the ecological value, and that's, in the previous exercise, you put it in the balance as something that has a cost if you remove it. What you can do post-remediation is do monitoring. You can do sampling, you can put monitoring stations there, you can look at the sediment that flows in the river and catch it from time to time to see if there's still contamination, if contamination still moves within the field. In fact, in the swamp I showed you, there is no remediation whatsoever. There they try to look at stabilization by making the land wetter, and so reducing the availability and the mobility of radium. So new techniques do arise, and it's important in innovation and in research to look at new techniques to make sure that BATNEC analysis is fed with sustainable circular waste options that can be applied in the field. You can also put recommendations out there. Again, don't eat the sheep you put on there. And restrictions, for example, recreation. If you have contamination that you left in the field, you can put restrictions on land use and so on. But again, there are different legal frameworks that might apply. In this case, radiation protection framework, there's the chemical framework, and you have to align them. And there are very different institutional stakeholders that all have their opinion about what has to happen. And so you have to align it. And in this alignment, perception of risk, and that's probably something that will be talked about or has already been talked about, is important. Because people will come to the table with their perception of what the risk of radioactivity is. If you mention radioactivity, then people panic, usually, if they're not well informed. And you have to be careful that you can't just say, no, the science says it's okay. The science says that there's no risk. Yes, but there's radioactivity, and we just want this radioactivity to be gone. So you have to explain the concept of background, natural background, and so on. And so the perception against the objective risk is something that is present at that stakeholder discussion, is always present in discussions you have with the different stakeholders. And all comes down to risk communication. How do I communicate a risk? How do I convey a risk? And that will influence how people deal with what they want to see after the remediation project. And so typically, the scientists at the table that calculate the risk are not the best people to convey, not always the best people to convey the message, because their risk perception is very low. At the other end, you have the public that has a very high risk perception, and you have to find a middle ground on and have to listen to each other and say, well, what is an acceptable risk? And that can be modified along the way, because this takes years to do, and sometimes along the way that changes. You can also have, and that's something additional. For example, in a lot of these sites have been there for years. So the people with a certain age have actually accepted, in some cases, situation. So people living there know about the radium, they accept that it's a very low risk, they know about it, and so they will be open to discussion. What we see in recent years is that, for example, a lot of people from Antwerp move to the countryside. So these are young people with children that go and live in the countryside. And actually you see that the discussion changes because they go and live there because it's green, it's nice, it's beautiful, it has healthy impact on their children. And then somebody from the region says, well, there's this metal concentration there and this metal contamination. I don't know if you knew about this. And they start to panic and they become very, very angry because, well, why hasn't nothing been done and so on. And this changes the mood at the table. And so this is, as I said, this is something that changes with demographics, with trends, with whatever is in the media at some point, because at some point in Belgium, everybody started talking about PFAS and so on. If I'm now I go to a meeting in a community talking about heavy metals and radioactivity, then it's okay, yeah, radioactivity, we know. What about the PFAS? So suddenly radioactivity is not the bad guy at the table anymore. It's just something we know we can manage. Just to say that science and your risk assessment is not everything. You end up as a scientist or as a communicator at a table with your objective risk analysis. And then it might just be, you might just find yourself in around the table with people that say, well, but this is all very well, but we don't accept that risk. And then you have to be prepared to deal with that. So as a conclusion, and I think I'm within my time, as a conclusion, you never have a radioactive contamination without other components. You have heavy metals, you might have other PCBs or whatever, because it's usually, especially in the case of norm, it's always a result of some process that dealt with ores or natural resources. So you have heavy metals in the entire periodic table there somewhere. That also means that in a complex country like Belgium, but there are other complex countries, there are federal countries, other federal countries in Europe, you might end up with a lot of institutional stakeholders. You might have different regulators, you might have different legislations for chemicals and for radioactivity, which is usually the case. And so you have to align yourself, not only with those stakeholders, but also with, well, like I just said, the local stakeholders. This is why this BATNEC analysis is very important. You have to weigh everything against each other. You have to weigh the cost of your actions against the cost of another possible option. And that limits the conflict between measures, because you have to look at it from different angles. If there's one main message, I think, for this presentation, is that looking at it from different angles is very important. And sometimes, and that's a very difficult message to convey in risk perception and in risk communication, sometimes it's best not to intervene. If you have very valuable ecological area, If you start digging, then that's gone. So then you start depending on what is the value people put on habitats directive, on Natura 2000 areas and so on, and you end up with another discussion. But sometimes, indeed, doing nothing and just monitoring is also remediation, because remediation means bringing stuff under control. Does the radiation protection assessment make a difference here? No. So we did this very complex radiation protection assessment. We've calculated it, and we said, well, nothing has to happen because there's no significant risk. So actually, it doesn't change anything. But once somebody else says, well, there is justification for remediation, then you have to intervene anyway, and you have to look at it anyway. One of my perceptions here, how does state organization influence decision-making for norm sites? I've put this in because this presentation comes from a conference where I gave this presentation first at a conference with a lot of radiologists that said, well, radiology and radiation protection is the most important thing. Well, yes, but if you have other types of contamination, there are other factors that might influence how you work, and state organization is one. We're in a federal state, so different types of contaminants are dealt with on different levels, and so you have a more complex situation. In, for example, a country like France, where a lot is centralized, everything might end up with the same regulator and with the people kind of integrated team where they take decisions. But obviously that makes it less interesting, because discussions are very valuable. And looking at radioactivity in itself, it's well, there is the history in a lot of sciences, but especially in ecotox, where radiation protection and radioecology has gone its own way after Chernobyl, after accidents that had environmental impact, and ecotox in general, which has dealt with heavy metals and other pollutants. And so in scientific research, but also at the regulator level, at the state level, these have been two separated worlds. And it's only the last 20 years that people have been learning from each other, that people from radiation protection are going to CTAC conferences, for example, or vice versa. And this is important because you need this interaction. You need concepts from chemical remediation, from chemical toxicity to seep into radiation protection, because ultimately you're dealing with heavy metals that are by chance radioactive. And so their chemical behavior is just the same as any other heavy metal. And so you have to make sure that you start learning from approaches. And especially in this case, where heavy metals and radionuclides are together, that's a very important lesson.